Hey everyone, I'll maybe give it a few seconds before we get started. I see people are trickling in. So I think let me get started while people are joining in. So hello everyone. Thank you for joining for our third round of Dissertation Jamboree. So far, we've had fantastic speakers talking about their dissertation research so far. And we'll have the recordings available on YouTube on those. And today we have two more fantastic speakers, um, Macon and PU Devanand, who will be talking about their dissertation research. Um, and before I introduce the speaker, just a couple of announcements from AGN SIG. This is something Travis yesterday mentioned about Ad Astra initiative, which is what COPAC is planning to host. It's a workshop that they're planning to host in September, and they're still figuring out the details. But if you're interested in and if you have any ideas about AGN science and how we can use new mission concepts or probe plus concepts to push forward the AGN science, please do reach out to Erin and Travis. And here is a QR code if you want to know more about the workshop. Um, a couple of more things that are happening in the next month from AGN SIG. We have AGN Coffee Discord discussion group, and here is a QR code, especially if you're a early career researcher, young folks who are interested in doing a more informal discussion on AGN papers. This is led by our wonderful Anika Goyal, and the next AGN coffee session will happen on May 7th at 1 p.m. Eastern on Discord. Link is also in the chat now. And we'll also have a vision series talk. In case you haven't seen this, we will have this vision series on May 26th, and it will be given by Dr. Stephanie Junot from NSF North Lab. With that, let me talk about today's speakers. First up, we have Macon Magno from Texas A&M, and he'll be talking about radio-quiet AGN. And then we have another person, PU Devanand from Aryabhatta Research Institute, who'll be talking about multiband studies of lasers. Without taking too much time, let me first start with Macon. Macon, please go ahead and share your screen.
Alrighty, let me share it. Can you see it? Or let me go full screen. Continue. You can see it?
Yeah, it looks good.
All right, perfect. So yeah, let me move that there. All right, so I'll move that there. Okay, so my name is Macon Magno. I'm a grad student at Texas A&M. I'll be defending in June. So this is a lot of this work is some of this is still in prep. My advisor is Crystalline Smith, and today I'll be talking about a complete census of the radio properties of radio quiet AGN in the local universe. So, what did that? There we go. So let's begin. So my overarching question that I'm trying to answer in my thesis is sort of what drives the radio emission in AGN. And so we could sort of break this up into two different questions. And so one question is that what physical processes contribute to radio emission and radio quiet AGN? So as we can see in this figure in the bottom left, there's several different components that can contribute to this radio emission and radio quiet AGN. Star formation could sort of dominate and sort of drown out the AGN. The corona of the AGN can contribute and sort of drive the variability there, along with the jet or wind and its respective shocks can also be a big component there. And oftentimes, what you'll have is sort of star formation mixed in with the corona, mixed in with some sort of outflow. And so, trying to disentangle that becomes quite troublesome and tricky. But that's something that we're trying to tackle, and hopefully, we make some good strides in that direction. The second question that I try to tackle is what's the relation between radio loud and radio quiet AGN? And so here we have a nice radio loud jet that extends on megaparsec scales. And so we're trying to connect and try to understand how these radio-quiet AGN sort of evolve or turn into these radio loud sources, or even are they the remnants of these radio loud sources? And so we're trying to make strides in these directions to sort of better understand how these AGN evolve over time. So to start, what better sample to start with than the 70-month SwiftBAT survey? So this allows us to, or the SwiftBAT survey sort of allows you to peer into the local universe and get a sort of an unbiased view of AGN, thanks to the fact that it can sort of peer into the Compton-Dick regime of these AGN. And if we look, my sample is primarily like Z of 0.05. So it's primarily in this little bottom right-hand corner, or bottom left-hand corner, my bad. And it's primarily swift bat detection. So we have a nice healthy sample here of all these swift bat sources within the local universe. Um, so, but I sort of came into the project in the third phase of the radio step, but in between the Swift and the radio, there was sort of this intermediate Herschel sample that underwent, and that was Richard Mistotsky and his grad students at the time, around 2014, sort of went out and observed 313 AGN. And so the main takeaway that I think is the best comparison to our sort of survey in the radio is that they didn't detect all their AGN. I think they had like less than a 90% detection fraction in the infrared. And so from that 313 AGN, we sort of sampled 231 of those, and that's sort of the entire Herschel sample that you could see with the VLA. And so within the Z of 0.05, so fairly local sources. And then at the time when they first started this survey, they sort of aimed for 1 arc second resolution because they were interested in the cores of these sources to try to understand if they were jetted or if they're what was going on in the central engines. To sort of achieve that, they had to choose 22 gigahertz or the K-band receiver on the VLA. And so this work has been published in that bottom left QR code. And within it, you'll find the previous two phases that Krista, my advisor, led. Additionally, all the 22 gigahertz images that we've ever produced, along with the 3 and 6 arc second images, are available on the GitHub on that right QR code. And if you need like some special resolution, like 2 arc seconds or 10 arc seconds, feel free to send me a message, and I'd be happy to process that for you and get that to you. But moving on, here's where you can sort of see the various radio images, which are the red contours overlaid onto optical. And you can sort of see in these top two that you have sort of a outflow-like morphology, indicating either a jet or a wind is sort of driving the emission there. But in these bottom two, you can sort of see that they have these sort of blobby structures to it, and it's somewhat hard to determine what's going on within them just from these 1 arc second images alone. So this sort of goes back to that first figure that I showed earlier that sort of shows the mixture of all those different emission mechanisms that can make this quite complicated. So one big takeaway, sort of stepping back to the Herschel sample, is that they had less than 90% detection fraction. Well, we had almost 100% detection fraction with only 3 sources non-detected within our survey. 2 of these sources, it turns out, sort of just are were just below our sensitivity limit. So I bet if we went back, re-observed them with a deeper sensitivity, we would recover them easily, which leaves us at 1 source. And we'll visit that source here in a bit. So, whoops. There we go. And so just going into the morphologies a little bit more, you can sort of see how we classified them into these various categories. So if they had some sort of linear structure or biconical structure, we called them jet-like. Now, just because we call them jet-like doesn't mean they're jetted in any way. They can in fact be wind driven, or even I think there was one source that I found out that was people were investigating as a dual AGN, but we classified it as a jet-like source just because it looked like sort of this one on the right, where it had 2 lobes here, and we were like, okay, well, it's biconical in some way. So that's sort of the nature of the jet-like sources. And then we also classified things based off compact, and that's fairly simple. If they were round and sort of beam shaped, then we sort of just called them compact and moved on. But if they were in between these two morphologies, we called them extended. And so just a fun fact about the morphologies here is that the extended and jet-like sources make up about 50% of the sample, and compact sources make about the other 50%. So odds are, if you were to go out and observe a nearby AGN, you got a coin flip to sort of resolve some emission, which is fun. and neat. But what is this emission coming from? And so here we have a nice little picture of the solar eclipse where you can see the sun's corona. Uh, and so this sort of takes us back. And so why are we talking about the sun's corona, right? But back in 1993, Goodall and Benz sort of explored the coronal relation for coronally active stars, and so it's a stellar relation. And then sort of did like X-ray radio relation, saw that they followed a line and published it. Then in 2008, Lahore and Behar sort of took this relation, which you could see here's the coronally active nature and stars from Goodall Benz's work in the bottom right on that bottom figure. They extended it out to radio quiet quasars, and so you could sort of see over these large magnitudes, it sort of fits a line. But in this top plot where their sample is, you can sort of see there's a huge amount of scatter. And this was at 5 gigahertz. Well, if we were to sort of step up and apply it to our 22 gigahertz sample at 1 arcsecond, we could sort of see that there's a trend there. We still have a scatter present, but the scatter seems to have dampened a little bit and a little bit better. And just a few notes about this plot is that these diamonds here are the radial loud sources in our sample. And so those are obviously going to deviate from this relation just because they have jets powering the radio emission instead of the corona. And in addition, you can sort of see our anomalous radio quiet sources down here, which sort of fall away from the bulk of the sample. And they should be somewhere up here, but for some reason they fell. So these are interesting sources in their own regard. And yeah, and we just have both bands of the Swift BAT and XRT. So where the relation still holds. But if we were to continue out to 100 gigahertz, where Claudio Ricci has done this work, you can sort of see that the relation sort of tightens up a lot, and this is at higher resolutions too. So he's really peering into the cores of these AGN, and so it's sort of like, okay, well, we sort of have a way to map out the coronas over many frequencies, and if in fact if you go out 230 gigahertz, the scatter sort of jumps back up, and it's not as tight as the 100 gigahertz scatter. So this sort of is like a pseudo SED that I've sort of presented to you. And we could sort of use this to sort of identify coronally active AGN in the radio and millimeter from this. So we're going to sort of talk about building up these SEDs to sort of build up and further push this work forward. And so here's just a little brief background on synchrotron emission and how it comes to be. So it's just a population of electrons that are spiraling around magnetic fields, and as they spiral, they will often self-absorb some lower frequency energy. And then if you have a superposition of all these electrons, you get a nice little power law. And eventually, if you are lucky enough in your SED, you can see that population of electrons sort of has like a general turnover frequency, and then you can get that. And if you do see peaked spectrum sources, you could sort of do a lot of neat things with them, such as deriving physical parameters about the magnetic field and largest angular size. With that, here's a nice little radio SED for M82, which is a starburst galaxy. And you can sort of see the synchrotron emission here. The free emission is sort of this flat spectrum. And then you got the dust gray body. And so what I've done is sort of take this sample of 231, expand it out to all as low as frequencies we can go, which is usually 70 megahertz, and sort of build into the dust gray body. And so that way we can sort of incorporate ALMA data and sort of account for dust in a meaningful way. And so some of the models that we sort of test for here are the power law, which is the most common that you'll see in literature, along with peak spectrums and different types of peak spectrums and a retriggered or restarted spectrum. In addition to this, we've expanded on Emily Kerrison's work by adding in multiple peaks to sort of account for like a possible low turnover frequency or and a higher frequency peak that can sort of happen. So you have sort of two peaks within the spectrum, and it sort of allows you to capture a possible coronal or a high frequency excess too. So here's one of the sources, Markarian 348, where you have a nice little restarted spectrum. And you can sort of see we take the different circles represent different resolutions, and we sort of have a resolution independent view when modeling these SEDs because we want to sort of see what the highest resolution is doing, and if it matches lower resolutions, then we could sort of, okay, so the resolution doesn't really matter for this source. But if it does, then we could sort of extrapolate and compare extended emission, like fit the lower resolution data and compare that to the higher resolution data and sort of try to figure out what that emission is coming from. But unfortunately, I don't have any of those to show today. But yeah, so this is a restarted spectrum. And so just to highlight the data, so the VLA covers this frequency range, but there's also many other telescopes you can use. The ALMA covers up to here, and then we have the far AR to the data from like Herschel and other satellites up to the right, and then low frequency coverage here on the left, where we can get stuff from LWA, Merchant Wide Field Array. And so by combining data from all of these, we could sort of build up these nice SEDs and sort of infer properties of these AGN. And so for reference, here's all the data that we've used within this SED itself. Um, so to sort of keep going, here's a peak spectrum of Markarian 6. What does this mean? Well, if we look at the radio images in the top, as you see flash through the of different frequencies and resolutions, you can sort of see there's an outflow there, and it sort of has like a sort of two component outflow. You sort of have a more diffuse one and then a compact bimodal structure in the middle. And so that's usually what peak spectrums imply whenever you find one, is that there's some sort of young outflow that's sort of, or a frustrated outflow within the middle of the galaxy or the AGN, and it's trying to form. And so these probably, it's been theorized that these are young precursors to radio loud AGN. Just give them enough time, and eventually they will turn into them. And so you can sort of see down here from Carb et al. The same images that I'm showing you in the movie, but you can sort of see they have a Merlin image which shows the VLBI jet on small scales. So apply that to a much fainter source such as NGC 1106, where it has a peak as well. And then we didn't have any high resolution data for this one, but we did, in an unrelated proposal, have a VLA configuration observation. We uncovered a jet or an outflow within this source, and sort of implies and backs up the fact that these peak spectrums sources can sort of give us information about the morphology of the AGN on small scales, which is neat. But sort of stepping aside from peak spectrum sources real quick, here's the non-detection I mentioned earlier. And so here we can sort of see it doesn't have much, right? It only has a bunch of non upper limits here that sort of imply that there is no emission. And then it has a nice detection at ALMA wavelengths of about 230 gigahertz and a far IR detection. So this is 1 out of 230 AGN, right? Which implies that most, if we were to extrapolate to the entire AGN population, most AGN will have some sort of radio emission within it. So what does this mean? Well, this source may be an outlier, and it could also be that just need deeper surveys too to sort of pull out the radio emission from this source. But it's also interesting that this doesn't have any radio emission when we expect most AGN to emit in all wavelengths, right? So going back to what we can derive from peak spectrum, we could sort of see that if we derive peaks in the respective peak flux densities, we could sort of derive the magnetic fields and largest angular size and compare that to sort of radio loud sources and what you sort of expect from them, especially the magnetic fields and what you see in their jets. We could truly test what we see against their magnetic fields. Next, we could sort of age these sources once you have the peak frequencies, which will allow us to see, especially for the restarted sources, you could sort of estimate how often are these sources active, right? And it's like 10 to the 5 to 10 to the 8 years a good estimate for AGN episodes, or is it something shorter or longer? So that's essentially the SED project, and that work should be coming out later this year or early next year. But now I'll be talking about sort of using water masers to trace feedback. And so throughout my thesis, we were sort of looking at water masers as a probe to study feedback. And we were interested in this because we see like O3, H beta, and H alpha lines that sort of trace these unique lines like double peaked and triple peaked emissions that trace outflows, right? And so we came across these sources and from the Mega Maser Cosmology Project that hadn't really been followed up. And primary reason is because Mega Maser Cosmology Project is interested in triple peaked sources in which they can sort of derive black hole masses and precise redshift values for the galaxies. But for like this source, it was published about in 2008 from Bratz and I don't know how to say that last name, but Bratz 2008. But with a nice little 600 kilometer per second offset, in GBT. And so this and sort of implies like it's high accretion rate, and that's what they said in the AGN or in the papers that it comes from the AGN's accretion disk. But when we observe it with the VLA, we see the same line, right? It's still about 600 kilometers offset. Uh, but if it was in the AGN's accretion disk, we would expect to see it in the continuum, right? Or in the core, right? But instead, what we see is that it's off axis about a kiloparsec away. And we uncovered the jet from that I showed earlier. Um, so what does this mean? Well, it means that AGN, well, first that the 22 gigahertz emission is from our 22 gigahertz atlas is consistent with whoops, sorry, let me start over. This means that the AGN can power water masers about a kiloparsec away and can sort of power these water masers and drive out gas from the galaxy, even though they're radio quiet and they have these small scale jets about 900 parsecs. Um, so these jets are fairly small, and it seems to be driving a lopsided uh, outflow, but it is consistent, and then we did find it about a kiloparsec away. Uh, so that's that. And so, in addition to this, we have five sources that we've been looking at. We have several other sources that show signs of outflow, meaning material that water masers are tracing. But we've also found this source right here, where you can sort of see in the GPT spectrum multi-peak peaks. And then when we observe it with the VLA, we see the same peaks. But if you look closely right here, this is a 53 to 5400 region, and we don't see really anything there. But this 52 to 5300 region right here is empty. So what does this mean? It sort of implies that the water masers or it implies like there's a rotation going on within this source, or there's an outflow moving on like some very small scales that we couldn't resolve because our continuum measurement sort of shows a compact source, and the maser was located entirely within that. So it's something interesting to further explore, and we hope to have this out within the next year too. So with that, I'll sort of stop here and yeah.
Yeah, you're getting plenty of applause. Yeah, thank you, Macon. This is a really great and impressive amount of work, especially with the VLA observations of 200 sources or so. Okay, we have plenty of time for questions for Macon. If you have any questions, please feel free to raise your hand or put the question in the chat and I can read it out. So any questions?
I can ask a quick question.
Eric, go
I
ahead.
wait for others to think. So thank you very much for this great talk. This was wonderful. I was wondering, so given you've used a range of facilities here, I'm just thinking about what we would need in the future from the
Yeah.
observational side to really take next steps in understanding these big science questions. Do you have any facilities you would want to see or capabilities observationally you would want to see us move towards to be able to take, really advance this?
Yeah. So I think one thing that I'll go back to the SEDs real quick, just to sort of emphasize. Um, so the like we've all heard about the NGVLA and SKA are coming online, and they'll have like this huge amount of collecting area that will sort of allow us to sort of break these SEDs up into, or at least each data point in these into multiple data points. And that'll be great for these SEDs so we can sort of resolve structure and within the SED itself instead of having like single data points spread across 8 gigahertz of bandwidth or so. So we'll be able to do that much more efficiently with the advent of those facilities. But in addition, I think like high resolution X-ray or like where you could sort of see sub-arc second, any like mission that can really peer into like sub-arc second scales would be great for this kind of work. That way we could sort of like when we go to uncover like jets, we can sort of peer into it with and sort of confirm like are these jets like bona fide jet material or is it something like a wind? And that'd be like spectra or I don't know if you could do that with continuum or photometry, but spectra definitely would be great for that. So you can extract velocities for what's going on around like these lobes. Uh, yeah.
Great, thanks.
Next, we have Mingy. Please go ahead.
Yeah, yes, about I mean, 1 kpc water maser offset from one of the galaxy NGC 1106. Yes, that one. Did you check, is there any star forming regions
Oh,
around that spot? Because I mean, the water maser in our inside our Milky Way, there are very
yeah.
common like high mass and low mass star forming
Yeah.
regions. But that is the extragalactic source. So
Yeah.
I expect it would be very faint. But I was thinking about maybe they're not like jet related, but we have to
Yeah.
consider about any like star forming induced in that locations. Yeah. Do you have
Yeah.
any
Yeah.
thinking
Yeah.
about that?
Yeah, that's a great question. So I think throughout the paper, so we just submitted this work about a week or two ago, and throughout it, we did like do a little comparison to like W3OH, for instance, which is in the Milky Way, and we find like if we were to make some assumptions about this water maser and that it was star forming related, it'd be way too bright, or it'd be one of the brightest
Yeah.
in the universe if it was a star forming driven maser. So we kind of ruled it out from that perspective, but we also don't have like any like UV imaging of this source to sort of verify if there was like a bright UV not there, then that'd probably rule it, bring back star formation back into the possibility. But
Mm-hmm.
I mean, this we sort of just took like the paper that we submitted sort of has more of a radio only focus on it, which is kind of, I mean, we looked through all the archives, like Hubble didn't have any data, and we couldn't get JWST time for it. So it's something that we'll continue to investigate there too.
Yeah, it's very interesting that part. And also it is only one, I mean, one point source in that
Yes, yeah,
water maze. Yeah.
yeah,
About the jet maser, I mean not I mean the jet maser
yeah,
in our nearby AGNs. The jet maser are more like
yeah,
several clumps, not only the single
yeah,
clumps. So yeah, it's very weird, but I'm very interested about it. Thank you
yeah,
very much. Yeah.
yeah, yeah.
Thank you, Mingy. We have a question in chat from Sarah. Sarah is asking, do you have any thoughts about time domain observations?
So I think time domain in the radio hasn't been, it's kind of hard to do. But I think that sort of goes back to what Aaron asked as well, is like, what can we look forward to in the future? And I think the VLA, I mean, you could do this with the VLA, ALMA, but you sort of compete and you're asking for a lot of time over the course of the observing semester. But I think with the NGVLA and the SKA, you could sort of time domain observations will become much more easily accessible, and just due to the large amount of collecting area, you could probably get take like an hour observation per week to down to like 30 minutes on source, or 30 minutes for the entire thing with the SK and NGVLA. So it's something to look forward to the future, but it's quite hard right now. Yeah.
Yeah, thanks. Do we have any other questions for Macon? We have maybe a minute before we can switch to next speaker. Maybe I can ask one
Yeah.
final question, Macon. Yeah, it's as I already said, it's a great amount of work with the SED modeling, and the maser work is really impressive as well. So for the three sources for which we do not have any detection,
Oh yeah.
I was really surprised. My question is, have you looked at any galaxy properties that can tell us more about why you're not detecting radio there? You know, are these
So
less massive galaxies? Is that why you're not seeing anything?
yeah, that's a great question. So I haven't, so the SED project still, it took me a lot longer to go through all the, like I went through a lot of archival data and VLA, reduced a lot of VLA data and collected a lot of ALMA data. So I haven't had a chance to get to that phase yet, but this source is like, this MCG source is the only one where we don't detect any like radio emission. It has like a millimeter emission from ALMA, but nothing in the radio. For the other two non-detections that I mentioned earlier, those do have like detections. I think they're both detected in like LOFAR and NVSS or FIRST, which are 1.4 gigahertz. But they're like faint in those surveys. So when you extrapolate like from just a simple power law down to our 22 gigahertz emission, it felt like I think we would have expected something like on the order of like a micro-Jansky emission. So it fell way below our detectable emission and got drowned out in the noise. But for this source, I have not looked at it at all, and it's something I plan to look into as we sort of gear up and wrap up like all the modeling. It'll be something that we'll talk about in the paper and sort of explore more. It could be, I mean, I don't know why the source wouldn't have radio emission, but it just hasn't been detected. It may be like NGVLA and SKA can uncover these fainter sources too. So
Yeah, you have a
yeah,
lot to explore once you pass your PhD work.
yeah, yeah,
Well, thank you so much again for giving a wonderful talk, and good luck with your dissertation that's happening soon. Is that right? In June?
yeah, yeah. It'll be in June 5th. Yeah, yeah,
All right. All the best.
yeah. Thank you.
All right. Let's go to our next speaker. We have PU Devanand. He'll be talking about multiband studies of HBL blazars. Devanand, please go
Yeah,
ahead and share your
sure.
screen.
Am I audible by the way?
Yes, we can hear you.
Sure, okay. Just a minute. Okay, is my screen visible?
Yes, it's looking great.
Okay, so first of all, I should thank the AGN SIG team for giving me such an opportunity for the same. And I'm Devanand, a PhD candidate from ARIES, India. So basically, what my studies is, uh, it's basically how the variability studies, let it be flux or spectrum, how they will help us to extract information about HBL blazes. So a brief outline of my studies as follows. We will see what are HBL blazes and how we can use XMM Newton data to do the flux variability study, spectral variability study, what are the information which we can gain from them. Then there would be a case-specific study of an interesting blazer, and finally we will come to a conclusion. So this is basically about the blazes. As we know, in case of blazes, they are jetted AGN with jets close to our line of sight, and they are known for their variations in throughout the electromagnetic spectrum due to the non-thermal Doppler boosted emission. And basically, the blazes can be divided into BLX and SSRQs. As you can see, there are two broad bumps in the SED of the blazes. The primary bump is associated to the synchrotron peak of electrons gyrating around the magnetic field, and the secondary peak in the widely accepted leptonic scenarios, it is due to inverse Compton scattering. So depending on the frequency in which the primary hump occurs, the BLAC objects can be classified into LBLs, HBLs, IBLs. So basically, HBLs are those ones where the synchrotron peak is in X-ray or UV region, that is greater than 10 raised to 15 Hertz. That brings us to the motivation of thesis. So usually the blazes show their variations are more prominent near the peak. So when we take the HBLs, their peak is around UV to X-ray. So they show more variations in that energy range. And the intraday variations, like intraday X-ray variation, that is less than a day, it will help us to constrain the size, physical condition of the jet emission region near supermassive black hole. On the other hand, spectral variation will give us clues about the acceleration mechanism or particle distribution. In case of XMM Newton, it has observed a large number of blazes. So the aim of our thesis is that we are doing a systematic study of HBLs observed by XMM Newton to improve our understanding of the jet physics, particle acceleration, and so. So basically, we have used XMM Newton for our observation, and XMM Newton has three science instruments, if you are familiar with it. One is European Photon Imaging Camera, which we primarily use for our work. It is used for X-ray spectroscopy and timing studies. We also use optical monitor, which is used to study in optical wavelength. So there are two types of EPIC camera, MOS and PN. The PN camera is more sensitive and it is less susceptible to pile up high effective area. So basically we use EPIC PN during our data reduction, and this is just a structure of EPIC PN and EPIC MOS. We are using EPIC PN for our studies. And this is basically a quick data reduction what we have used throughout this work. We can obtain the raw data from HSARC archive. Then there is SAS. SAS stands for Science Analysis System. It is basically a collection of scripts tasks to reduce the XMM Newton data. And using that, we will create calibrated event files. Then we have to search them for the proton flaring. If there is proton flaring, we will remove those intervals which are affected by proton flaring. Then we can select the source and background region. After that, there is something called pileup, which happens for the brighter source. If there are sources which are affected by pileup, it can be visible again using some task. We will remove a central portion and then redo the task again, and it will help us to generate the light curves, which can be used for timing studies. In case of spectra, we will generate the source, background spectra, and some other files like RMF and ARF file, and we can use it to study spectra. So basically, our work consists of 2 population study and 1 sample study. Our first study involves, we studied 10 HBL sources, which spanning around 54 observation. And second study have 13 sources spanning across 54 observation. And the last one is like a sample specific PG 1553, which has large number of observations. This is our basis of timing studies. What we have basically done is that this study was concentrated on 10 HBL spanning 25 observation. We created the light curve of them in 3 different energy bands, like total, soft, and hard. These are the light curves which we have generated, sample light curves. From the figure, you can see on the top, these light curves looks variable. At the bottom ones are non-variable light curves. But you can see the error bars of them are large. It means their errors are significant. So even if visually they are variable, they might not be variable statistically. So we use different analysis technique to see if the variations are real and to quantify variation and to do other analysis. The basically first one is excess or fractional variance, which will remove the noise component and we will get true information whether the light curve is variable. Then we can also do minimum variability timescale estimation. That is the minimum time in which there is significant variations. There is discrete correlation function. It is basically used to compare 2 light curves. Let's say you have soft and hard. We can cross correlate or we can compare them and see if they are varying at the same time. If they are not varying at the same time, we will find lag at some other time. Then there is hardness ratio analysis. It is like a rough method of seeing if there is spectral variation with time. That is, if the hard and soft counts varies with time. There is also power spectral density to search for QPOs, if any. And this is basically the results of what we have got. It's a tabular form, it's confusing. So the results are summarized below. We find that 16 observations were variable, at least in any one energy band. Some of the places, like 3 of the places, did not show any variability, but all other 7 places did show variability. And for them, we estimated their minimum variability timescale. It was in the range 1 to 5.60 kilosecond. And from ACF, that is the cross correlation study, if we are limited to the same sample, I mean same light curve, we can see if periodicities are there in the light curve. So this is like a sample ACF plot. We can see peaks in 0. If there was any other peak, it means that there is periodicity in our light curve, which we obtained. So there was no periodicity. And we also looked for cross correlation. That means if the soft and hard bands originate from the same electron population. For 2 sources, we find that the soft and hard population, they are not correlated. That means they are produced from different electron population. And this is like a sample DCF plot where the peak is slightly offset from the 0. Again, we did the spectral variability studies using hardness ratio. Our study shows that for most of them, there is no much spectral variation with flux variation. However, for 2 or 3 of them, there are significant variation, which is visible from the table. Here we have the reduced chi-square at 99% significance and reduced chi-square when we're comparing it to the mean. For 2 of them, they show significant variations. And this is an example of like a hardness ratio light curve, which is not significantly variable and which is significantly variable. Then there is power spectral density. It basically shows that the low frequency is dominated by red noise and there was no presence of QPOs. Now, coming to discussion part, like in AGN, the variations are usually explained by relativistic jet-based model and accretion-based models. But in case of blazars, the relativistic jet is the most prominent one. So we have already estimated variability timescale. Now, using a simple causality statement, we can constraint the size of emission region. And we also have this thing that the synchrotron cooling timescale, it cannot be larger than the variability timescale. So using simple equations, we can put constraints on the magnetical field or in the region of the emission, the maximum electron Lorentz factor, and the maximum energy of the gamma rays which can be produced. So what we basically done is that we were able to estimate these factors for the all 7 blazes, and that was the work which we obtained using the timing studies. So basically coming to the conclusion, we find that from timing variability studies, we were able to estimate the constraints on size of emission region, magnetical field, maximum energy of the gamma rays produced. We find for 2 cases, soft and hard bands are not correlated. And hardness ratio analysis shows that in most of the observations, the flux variations are not accompanied by spectral variations. Our next study is basically spectral variability studies of HBLs. So usually the spectra of HBLs was initially fitted by power law. The reason for that is that there is synchrotron emission, the electron population of the synchrotron emission is power law, so the photon spectrum would also be power law. But later, the researchers find that the X-ray spectrum is in fact curved. And this log parabola model was introduced by Landau et al. And he was able to, this model was able to demonstrate this curvature. Many researchers followed it, but the physical interpretation for the same was provided by Massaro. So what he basically told is that the photon spectrum is curved because the underlying particle distribution is curved. This happens under statistical particle acceleration scenario, where the probability of particle to gain energy is decreasing function of energy. That means the more energy it has, the less chance of it to get accelerated. So basically in this study, what we are doing is that using XM Newton, we are seeing if the spectra of HBLs are curved or if they are fitting by power law or some other models. So this is basics of spectral fitting. I'm skipping this. So basically we fit the X-ray spectra with 3 different models. One is power law model, one is log parabola model, one is broken power law model. And all of these are convolved with the galactic absorption to account for the galactic absorption. Basically, each spectrum we initially fit with power law and log parabola model. And what we see is that we take the null hypothesis as the power law fits the spectrum well. So we compare the power law with log parabola using symbol F test. And if we get a p-value lesser than 0.01, it means that the log parabola model describes the spectra well. In the reverse scenario, if the p-value is greater than 0.01, it means that the power law model is sufficient. And in those cases in which we get a negative curvature, in other words, a concave curvature, we will try fitting broken power law. And for log power law, for log parabolic fits, we can derive the synchrotron peak height, synchrotron peak luminosity, everything by fitting EP log par model. So this is basically the results which we have obtained. I will show it in the form of figure. This is basically a spectral plot which we obtained. Here on fitting the power law, you can see the bottom one is the ratio plot, and this is the power law, and the magenta represents the log parabola. There is not much difference between power law and log parabola. That means the power law model fits the spectra well. This was the case for 14 of our cases, and we get photon index in the range of 1.78 to 2.68 for different blazes. However, for some other sources, as you can see here, when we fit the power law, there is a curvature at the low energy and high energy. And when we fit the log parabola, this curvature vanishes. That means here the spectra is curved. And this was what we obtained for majority of our sources. It indeed shows that the X-ray spectrum of HBLs in most of the cases were curved. We also tried to do some correlation study between different parameters. Here beta is the curvature parameter, alpha is photon index, this is just the spectral flux in 2 to 10 kilo electron volt. And these are the results of our spectral study. Since we have not that much observation for each source, there is still questioning regarding the authenticity of these results. But in most cases, we find there is a negative correlation between spectral flux and photon index. This basically indicates that there is injection of hard electrons. And then in one case, we find there is significant negative correlation between spectral flux and the curvature. It means that when the spectral flux increases, there will be more efficient acceleration, and basically the curvature reduces. We also find a negative correlation between the synchrotron peak and the synchrotron and this curvature parameter. Now coming to important results of our work. For 8 of the spectra, when we fitted the power law model, what happens was that there was like a high energy tail. So usually this high energy tail, when we fit a broken power law, it gets rectified. So in case of HBLs, as I told, the X-ray is mostly produced by synchrotron. However, when it comes to IBLs, which is intermediate synchrotron peak BLX, the X-ray region is like intermixing of synchrotron and inverse Compton component. So basically, what's happening here is that these HBLs, for some instance, they are acting like IBLs. So such a behavior was previously reported for another HBL PKS 2155-304. And basically, what we are going to see is that we are seeing if such a trend is there for this BLX as well, this HBLs as well. So we analyze their Morse spectra along with the PN spectra and see if they follow the similar trend. And these are our most of the observations. For 6 of the observation, when we see the Morse spectra, we can see that a power law provides adequate fit. There was no high energy and or there was no need of broken power law fits. That was the case for most of the observations. However, for 2 observations, we find that there is significant, I mean, these are the observations with strong conclusive tail. Here you can see in each MOS 1 spectra, PN spectra, everywhere there is a high energy end towards the higher energies, and by fitting the broken power law, it gets rectified. So we are telling that there is signature of inverse Compton component in this observation. This is only the second instance in which an HBL from an HBL we get the signatures of inverse Compton component. And basically, this is the results of this study, where we find most of them are fitted by the log parabola, and we estimated the synchrotron peak energies. We also find 2 observations with strong signatures of inverse Compton component. Then we come to the next source. This source is PG 1553 plus 113. It has large number of XMM Newton observations. Out of this, 30 are usable XMM Newton observations. However, we cannot go to high energy end of this source because there seems to be high background contamination. So we limit our study up to 7 kilo electron volt. And what we basically did was that we did like the previous work. We fitted it with power law and log parabola. We see that half of them favored power law, half of them favored log parabola. And these are some best fits in power law and log parabola. But one interesting thing which we found is that in all this observation, the synchrotron peak was found to be below the X-ray energy range. So what we did was that we tried fitting optical data together with X-ray data. Initially, it resulted in large chi-square values because these are 2 different instruments. So we introduced a 3% systematic errors to optical monitor data to account for the uncertainties, calibration issues, and we were able to get stable fits, and we did estimate a synchrotron peak in UV energy range. And this is like a fit of the optical monitor and PN data. And similar to the last work, we also see if there is any signatures of inverse Compton component here. And we found that there are 2 observations with significant, where there are significant inverse Compton curvature. For example, here in all these plots, the black represents the power law. You can see an high energy, and this is the same observation observed from different cameras like MOS 1, MOS 2, and a combined PN and MOS. And this gets rectified on fitting broken power law. So this is the, like the 4th source in which we are detecting the inverse Compton scattering. And so that's basically the results which we have obtained. And so on spectral study of PG 1553, we found that half of them to be fitted with log parabola, half of them to be fitted with power law. We estimated the synchrotron peak in the UV energy range. We obtained 2 observations to have strong signatures of additional inverse Compton component. And this is basically the summary of study. From the flux variability studies, we were able to constrain the magnetical field, electron Lorentz factor, size of emission region. From the spectral variability studies, we were able to estimate the synchrotron peak. We were able to find the components of inverse Compton scattering in 3 of the sources. And all of our work have been resulted in publications in APJ. So I guess that would be all. Hello.
Yeah, sorry. I was looking for my unmute button. Thank you so much, Devanand. This is really
Yeah.
great work. Lots of applause. Any questions for Devanand? Please feel free to raise your hand or put your question in the chat, and I can read it out if you want to go that way. Okay, Mingy, please go ahead.
Yes, very interesting about you showing the two sources, the hard band X-ray, soft band misband. They're the cross correlation. They're not. I mean, they're referred from a different electron component. Do you consider about the obscuration of the soft X-ray band? They were creating this kind of behavior, or you're thinking they're just intrinsic referred to different part of the electrons?
Because since we are looking at the blazes, mostly it would be jets, so I don't think obscuration plays an important role here. I thought there might be different electron population because if it's any other sources, I would agree with you. Since we are mostly dealing with blazes, the chances of obscuration due to torus or some other things are very low, at least to best of my knowledge.
Okay, thank you very much.
Any other questions? We have plenty of time. Erin, please go ahead.
Thanks. So that's the same question I asked before. So the information that you can
Yeah.
glean from studying the variability is really impressive and exciting. Is there anything you would want to see for observational capabilities in the future to help you advance this science and learn even more about blazars and other objects of similar
Yeah.
characteristics?
Yeah, actually, in case of blazes, the variability is very important. So let it be short term, I mean, like intraday variability, which where the variability is lesser than 1 day, or short term variability, where the variability is within weeks or months, or long term variability. So it would be good if there are some, let's say, coordinated observations of some any famous blazes. I'm not talking about just XMM Newton. Let's say because XMM Newton will help to cover up to 10 kilo electron volt. If there is new star, which will help to cover up to 70 or 80 kilo electron volt. If some at least 5-10 famous blazes, if we can monitor them, let's say once in every month, simultaneous, this will provide us more insights, like where is the tail of this synchrotron happening. So I guess that's one point. I mean, I would like to work in that field as well later. I mean, there are some observations like coordinated observations, but they are very few. So that's one point which I would like to raise.
Yeah, coordinated observations are quite important. Thank you for that point.
Yeah.
Do we have more questions for Devanand? Going once, twice. Okay, if not, I think we can finish a few minutes early if that's okay. All right. Well, thank you, Devanand. I know it's quite late in India, so we really appreciate you taking the time and presenting your research, and all the best for your PhD work. And also thank you to Macon and Devanand, both of them. Let's thank both our speakers for their impressive talk today. And we will see you all next time in May for our vision series. Bye, everyone. Hello? I think
Hello.
it's just us.
Pause. Yes.
I think I'm just
Okay.